Let's try a quick quiz. These pictures show the aftermath of 4 different disasters: a tornado, an earthquake, a hurricane, and a flood. Question is, which is which? Just pause the video for a second to figure it out. Okay, not too hard, was it? Answers will be at the end. But how do we know what caused these events if we weren't there to witness them? Make it up? Or do what you did with the photos and look at the clues that these events leave behind. After all, deducing what happened in the past is a process we go through every day. If we weren't there, we have to work it out by observation and deduction. Each sedimentary rock on Earth, for example, tells the story of how it was formed and under what conditions. Geologists can identify ancient earthquakes and floods just as you can identify recent ones. For thousands of years, Europeans assumed the rocks had all been laid down in the Noah's Ark flood. But in the 18th century, early geologists took a good look at the rocks under their feet and were amazed at what they found. Many of the rocks they saw were in layers and made of the sort of material you'd find at the bottom of the sea. Okay. But why were some of these sedimentary layers at odd angles, or on mountain tops, or bent out of shape? Why were the layers made of different materials? Underneath the top sedimentary layers, the picture got even more complicated. In 1788, the man called the father of geology, James Hutton, saw a geological formation that seemed impossible. At Sycamore Point in Scotland, he found this set of almost horizontal sedimentary beds sitting directly on top of an almost vertical set, and this formation wasn't unique. It's called an angular unconformity, and geologists soon found angular unconformities all over the place. By the mid-19th century, 2 principles had been established. It was clear that sedimentary beds that were once at the bottom of the sea must have been uplifted. Of course, the effect of these uplifts, and their opposite number, subsidences, are enhanced by the rise and fall of sea levels as polar ice caps grow and melt. But a rise in sea level alone doesn't explain how sedimentary rocks can be folded and lifted several miles high. Some unseen force was acting on them. Once uplifted, the rocks are subjected to erosion by wind and water. Silt, sand and mud are washed into the rivers and out to sea, where they're deposited, slowly building up the sedimentary beds that'll become the rocks of the future. So angular unconformities weren't that weird after all. The lower beds were laid down under the sea, with material eroded from the land. Over time and under pressure, water percolated through the deposits, precipitating minerals that cemented the grains together. Then the solid beds were lifted up and deformed. Now above sea level, wind and rain eroded the rocks, forming a soil at the surface. After a period of time, sea levels rose and covered the beds once again. More sediment was laid on top. Then the sea levels fell and the beds were exposed. Nearly every feature they'd seen in the rocks of the past can be seen in the deposits that are being laid down today, showing that this was a long and continual process that took millions of years. So early 19th century geologists had to forget their preconceived ideas. Instead, they followed the evidence. But although they understood erosion and sedimentation, the frequent uplifts were a puzzle. By observing and analyzing the rocks of the Appalachians in the 1850s, American geologists deduced that a deep trough in the ocean floor had accumulated sediment over millions of years and then been violently uplifted. They called this trough a geosyncline, and they soon found other mountain ranges in the world that had been formed in the same way. But they still had no clue as to what caused them. Then, in the 1960s, researchers made a discovery that transformed our understanding of the Earth and its geological history. The theory of plate tectonics concludes that we live on pieces of crust floating on partially melted rock as they drift around the Earth's surface. It's likely these crustal plates are driven by convection currents in the Earth's upper mantle. Thicker crustal plates, made mostly of granite, make up our continents. The oceans mostly fill the lower and thinner crustal plates, made of basalt. In some places these plates are moving apart, and new rocks well up from the Earth's mantle to fill the gap. In other places they slide alongside each other, and elsewhere they collide, buckling at the crash site and throwing up huge mountain chains. Now the uplift could be explained, and it fitted exactly with the geosyncline model. The deep troughs were, in fact, the boundaries between oceanic and continental crustal plates, accumulating sediment over millions of years. As the ocean closed, it brought two continents into collision. Thanks to precise GPS measurements, geologists can now see the process happening. The continents are indeed moving at about the speed your fingernails grow. As Africa and Europe collide, the Alps rise about 1 millimeter a year, and as India and Asia collide, they force up the Himalayas 5 times faster. Plate tectonics also showed that earthquakes are caused by buckling and jarring along the edges of the crustal plates. So if we look at the Earth today, we see processes that fit perfectly with the rocks we find from the past. We can see and measure uplift, identical to the uplift of the past. We can see how material is slowly eroded and deposited, and it matches exactly the deposits of the past. We can even see the same patterns and layering of the rocks today as in rocks millions of years old. Sometimes the sedimentary patterns are repetitive, if, for example, deposits are laid down in a seasonal cycle. Sometimes currents are gentle, and the sediments show distinct rippling. Shifting ripples in stream deposits and sand dunes lead to a structure called cross-bedding. And we can see the result of floods. Annual floods, catastrophic floods, local floods. Each type of flood leaves its mark and leaves clues as to how strong it was, how long it lasted, and what sort of material it carried. We can see a number of different floods at different times in the past, going back hundreds of millions of years. And finally take a look at this place, the Peak District of Derbyshire in Britain. Several meters down there's coal, which is the compressed remnants of a hot, swampy forest. Go further down, past a layer of hard grit, and we find a coral reef, which means that further back in time this cold moorland was once a warm, tropical sea. The reason is simple. The evidence shows that around 350 million years ago, the European crustal plate was much further south, and low-lying areas were covered by a warm coral sea. Then sea levels fell, the area became a river delta, and the coral was buried under sand and gravel. Millions of years later, sea levels dropped further, and the delta turned into a swampy tropical forest. Over the next 100 million years, the European crustal plate moved slowly northwards to its current position. So to geologists, there's no puzzle as to why we find the remnants of 3 completely different environments in the same location. It fits perfectly with what we know about crustal plate movements, erosion and sedimentation. Now let's go back to the quiz at the beginning. Unless you recognize these pictures, I can assume you weren't there when these disasters happened, and neither you nor I witnessed them. But just like the geology all around us, each of these photos has clues, and by using our frontal lobes, the reasoning parts of our brain, we can indeed work out what happened in the past.